Hi all. Today we see a paper titled Unraveling the Performance of Physics-Informed Graph Neural Networks for Dynamical Systems from IIT Delhi. So what this paper says is graph neural networks and physics-informed based deep learning have taken a much attention recently to simulate dynamical systems. And there have been many attempts to combine these two approaches. Here in this paper, they evaluate the performance of 13 different graph neural networks based on physics from Hamiltonian, Lagrangian, and neural ODE based, and their variations with explicit constraints and different architectures. So all these physics-informed graph neural networks could have an ability to exhibit a zero-shot generalizability to system sizes an order of magnitude larger than the training systems, thus providing a promised route to simulating a large-scale realistic systems without necessary to train those large systems and can be generalized from small-scale system to large-scale systems. So in the introductions, they say that there is an importance of physical systems and their modeling in areas of physics, engineering, mathematics, and biology. And those mathematical modeling of the complex physics system could be expressed in differential equations with respect to the state variable like position and velocity. And these differential equations can be easily solved using conventional numerical methods provided with initial and boundary conditions to predict the future state of the systems. And in many cases, however, the differential equations is quite unknown. More specifically, the knowledge of the force functions or the energy functions appearing in that differential equations cannot be directly measurable and cannot be obtained in a closed form and to complete the differential equations. So therefore, MLPs and data-driven models can learn the dynamics directly from the observed measurement data or time sequence data called trajectory. So the data-driven systems can significantly enhanced if if those MLPs are replaced by a physics-based deep learning models or physics-based data-driven models. And these physics-based models can lead to a realistic realization of the trajectory of system with a limited computational budgets. So in this paper, they observed that these physics-based systems can be based on Lagrangian neural network, Hamiltonian neural networks, and neural ODE, which has recently got a large attentions. And as like conventional MLPs, these training can be purely based on the trajectory of the systems. However, one of the key limitations of these models is this can be only for applied to a systems where it is trained for. For example, if the system, if the models are trained only for double pendulum, it won't be working for any n pendulum systems. So one of the key areas this paper tried to address is the accounting of the topology of the system in the graph framework using a graph neural network. And hence these graph neural networks, once trained, has a capability to generalize to an arbitrary system sizes. So these physics informed graph neural networks can be trained at node level, edge level, which can potentially learn more efficiently using the same number of data sets and for the same number of training epochs. So the author claims that so far there hasn't been any systematic benchmark their performance of these physics-based graph neural networks are mimicking the dynamics of the physical systems. Here they try to evaluate these different physics-induced graph neural networks on trying to learn the dynamics of complex systems like n-spring systems and nonlinear pendulum system, gravitational bodies, and elastically deformable 3D solid. So the contribution is of this paper is mainly have these 5 points. They have some kind of a graph neural networks which has physics informations embedded in that architecture, and they also try to use the physics constraints, and also they make use of the decoupling of the systems, mainly in terms of decoupling the potential and kinetic energy. And the last, the main important thing is they can generalize to arbitrary system sizes and order of magnitude larger than the system they have been trained on. The section 2 describes the basic learning dynamical systems, which can be expressed in terms of ODE-based formulations. These ODE-based formulations can be expressed like in equation 2, and if it is having a certain constraint, then it can be expressed in terms of equation 5, where the acceleration can be computed. And then once the acceleration has been computed, it can be double integrated to find the position and velocity. So the Lagrangian based formulation can be expressed in equation 7, and the constraint of Lagrangian formulation can be expressed in equation 9. And similarly, the last one is Hamiltonian dynamics, which is unlike the second order system of Lagrangian and the ODE based. It's the first order systems, and the expression can be given from the equation 11, and the constraint system can be expressed by equation 14. So based on these 2.1, 2.2, 2.3 physics-based formulations, we can formulate. There are 12 13 varieties of graph neural network formulations. One is fully data-driven full graph neural network. The next one is ODE-based graph neural network, and the next one is uncoupled ODE-based graph neural networks. The other one is constraint-based graph neural network of ODE formulations and decoupled formulations. Similarly, we can base similarly like unconstrained or constrained, coupled or uncoupled Lagrangian based graph neural networks, and also the lastly the Hamiltonian based graph neural network with constraints and unconstraints and coupled and uncoupled, and totally we have some 13 different architectures. And these architectures are coded in a JAX environment with the JARF package, and all these codes are available in the GitHub repository, which is being highlighted here. And the data were generated using these packages, and those generated data were used for training these different models with the loss functions expressed in equation 15, where the hat one is the computed output and the without hat is the ground truth data. Here the output would be the accelerations, and from those accelerations, once we integrate using the equation 16, we can obtain uh, the predicted position vector as expressed in this mathematical expressions. So they have some 10,000 data points for each dynamical systems, and 75% are used for training, and 25% are used for validations. And they make a fixed computational budget of 100 epochs, and the last criteria would be of 10 power minus 3. And the evaluation metric is one is relative error, and another one is metric error, momentum error, and the another one is an energy based error, which is expressed in these mathematical expressions. And for pendulum system, the three link pendulum system was used to train all these 13 different models. And for spring, 5 link system was used for the spring-based systems. And this would be used for to test case of the 4-link systems and 5-link systems. And these are the results we obtained for the constrained without constraint systems. And figure 4 and figure 5 are related to the 3, 4, 5 link systems for the pendulum and spring, pendulum in bottom and spring in top. And this is the left one is the rollout error, the right one is the energy conservation error. And we could easily from the see from the graph that Hamiltonian based decoupled system could exhibit minimized error among other models. And as we know that the fully connected data driven models has maximum error, and it's not no surprise that it has doesn't have physics embedded in it. The learning for a computational set budget is quite high compared to the physics based systems. This also continues to be the same for the pendulum systems. And when it comes to the constrained systems, when we try to use of the constraint with the explicit constraints, again the performance of the Lagrangian system seems to be very low and gives a maximum error. The reason would be that it has a double derivative compared to the simplistic model of a Hamiltonian, which has a single derivative to train the model. And the final, the main contribution would be, can it be generalized to a large system size for pendulum using 5, 10, 20 link pendulums, and similarly for a spring like 5, 20, and 50 link pendulum systems. Again, when we try to see the results, there is no any additional error added to any of this model considered due to zero shot generalizations. This confirms the superiority of the physics-informed graph neural network over the traditional MLPs to generate large-scale reality system after learning on a significantly smaller systems. So the final concluding insight would be that they build a graph neural networks, and they injected some physics information to build those network, and also they try to utilize some explicit constraints, and also they added some decoupled versions to build a model graph neural network models. And they showed that the graph neural network models could make a generalization to a large systems without training them, and even the errors are more comparable to the trained smaller systems. And also they identified that the Lagrangian systems have some challenges compared to the Hamiltonian system. The future would be that try to build architecture which are more robust to input noise data, because that there are some data have cannot be collected uh, from the true physical system, where we cannot be able to identify, and some measurement noisy data has to be utilized for the training. So the architecture has to be robust enough to accommodate this noise. So that would be something that has to be tried out in the future as per this paper. So thank you very much.